Hello. In this video, we're going to have a change of the guard. We're going to do some reviewing. And we're going to do some review examples. So take the limit as x goes to 1 of this guy right here, square root 7x plus 2, and then outside minus 3 over x minus 1. How would we handle that? Notice as x gets close to 1, the denominator and the numerator alike will get close to 0. The denominator you can tell. The numerator, well, if you let x, as x gets arbitrarily close to 1, 7x plus 2, well, 7x gets close to 7, so we, as a whole, on the inside, we get we approach 7 and just plain 7 plus 2, which is 9, but the square root of 9 is 3, and 3 minus 3 is 0, so the numerator also approaches 0, so we're approaching form 0 over 0, but that's undefined, okay? That doesn't really tell us anything. So how do we handle that? Here's what we do. When you see a radical, a lot of times what you'll do, I call it conjugate. I multiply the top and bottom by a so-called conjugate, or an adjustment term, whatever you want to call it. What I do is instead of, I got to keep the original things I had here, the two originals, but I insert on the top and bottom the term radical 7x plus 2, closed radical, plus 3, and the same thing down here. Instead of a minus in the middle, I've got a plus. Why do I do that? It has to do with difference of squares and FOIL and all that. I want to rationalize the numerator, which I know in algebra you were probably used to doing the denominator, but there is merit sometimes in doing the numerator. In this example, we'll see that merit. Well, now here's the deal. By difference of squares, you remember a minus b times a plus b is a squared minus b squared. Again, a minus b, a plus b, a squared minus b squared. So here's a squared right here. Here's b squared right here. Now the bottom, just leave it alone. Just leave it as is. Okay. And then now down here, we do, well, but if you, we take a note that if you square the square root, you just get the original guy himself, namely 7x plus 2, as is. So we have 7x plus 2 minus 9. Notice there's no more radical. That's good. That was the whole point. Now down here, we're just sort of stuck with what we got. Now going here where my cursor is, follow my cursor. Don't worry about the box in. Just follow my cursor. So now 7x, the plus 2 and the minus 9, remember by algebra, that's minus 7. So that's 7x minus 7 over this guy down here. Now we're still not completely satisfied because we still get 0 over 0. A 0 on account of this guy up top, for the top, and for the bottom on account of x minus 1. X is zoning in on 1 after all. But here's what we do. We filter a 7 out. By algebra, we can factor out that 7, and we get x minus 1. 7 times x minus 1, parentheses, in fact, up here where my cursor is. And then now down here, I'm still not going to do anything yet. So now here, but now what do I have next, though? I have, well, this next step, actually, you know what? I need to delete this. This was a waste of time here, because I didn't do anything. So just ignore this step right here, and I'll delete this guy a little later because I didn't really go anywhere. But what can I do? Let me get rid of... Okay, so now what can I do next? You see this x minus 1 here and this x minus 1 here? They cancel. And I just get 7 by itself up top, and then this guy down here on the bottom. You know what? As x zones in on 1... you know, neither one of these guys zone in on 0 now. That's good. Now, and because that's true, because the denominator does not zone in on 0, well, neither does the numerator, but in particular, because the denominator does not zone in on 0, we can say that the limit of the quotient is the quotient of the limits. Okay? And we can, by continuity, or else you could just say by the fact that... well, we have continuity, so the limit of the quotient is the quotient of the limits, and we assume continuity for radicals. We assume that the products and quotients and radicals of continuous functions are all continuous, so we can just throw 1 directly into here, and we get 7 times 1 is 7, and 7, then just do plain 7 plus 2 is 9. That's just radical 9 plus 3, but radical 9 is 3, radical meaning the square root. So 3 plus 3 is 6. So we get 7/6. Okay, and if you really want to be super complete, when you get past this step right here, you can say the limit of the quotient is a quotient of the limits. Then you can bring the limit inside. The limit of the radical is the radical of the limits. You can bring the limit inside the radical. But I didn't want to go through all that for this example. I just wanted, I'm assuming continuity for all this and just throwing one into here by the assumed continuity, okay? So there's that. And just to recap again, now let's go to a different example. The limit as x goes to 0 plus from the right of the sine of square root of x over the square root of x. That's the limit as y goes to 0 plus of the sine of y over y, which is 1, where we make the variable substitution y equals the square root of x. And after all, as x is going to 0 from the right, y is also going to 0 from the right. Okay? So there's that. And now here's another example, and this is going to beautifully illustrate why. You remember a while back we assumed that if I just had an x down here instead of an x squared, the limit 1 minus cosine x over just plain x, that would equal 0. But of course now we're not dividing by plain x, we're dividing by x squared. We can't assume that, and in fact it's not true. This is going to be a very pretty limit. Now remember, we do a conjugate again. We multiply top and bottom by 1 plus the cosine. We do difference of squares up top. We get 1 minus the cosine squared. That just means the square of the cosine. And then we don't mess with the bottom just yet. We leave it alone. But remember, 1 minus cosine squared from trigonometry, that's sine squared. So we have sine squared over x squared. Okay. And now here's the thing. What about that 1 plus cosine x? We can't just disregard it completely, not yet. Or actually, no, we're not at all, in fact. So remember, the limit of the product is the product of the limits as long as everything is non-zero. And that's going to be the case here. By continuity, the cosine of 0 is 1, and 1 plus 1 is 2. So this guy is not going towards 0, so we can yank him out here. So the limit, we can just yank this guy out. I sort of did 2 steps in one there. So I turned the limit of the product into the product of the limits there. But hey, remember the limit of the square is the square of the limit. Actually, I've not got to that part yet. So this is just the limit of this guy squared. For any fraction, a squared over b squared is a over b squared. So the limit is still not in the square yet. But here I just go ahead and utilize continuity, throw 0 into x, like that. So that's just 1 over 1 plus 1. Cosine of 0 is 1, but 1 over 1 plus 1, that's naturally 1/2, because 1 plus 1 is 2 down here. So that's a half. Now here we go. Here I do it. The limit of the square is the square of the limit. Here I make that golden step. I take that liberty. Okay? And so but hey, we know what this limit is. You remember we assume without proof that this limit is 1. So that's just 1/2 times the square of 1, but that square of 1 is 1, and 1/2 times 1 is a half. So my final answer is a half. I went ahead and just jumped straight to a half. I was still relatively tender. I didn't skip too much. Now let's go to the next example. Limit x goes to 0 of this guy. Well, now be careful. This time it's a different manner, because this is x squared in here. The other example, we just had x in here, okay? Watch out. This is really, would be a better, for this example, it would just be better if I did a variable substitution. I'm going to let y equal x squared. So as x is going to 0 from either side, y is going to 0 from the right. So we do y to 0 plus, and I do 1 minus cosine y over y. But hey, that we know from the earlier videos that we assume without proof that is 0, okay? This is another fundamental thing we're assuming. In fact, we assume the overall limit is y, like the general limit, let's just say p goes to 0 of 1 minus cosine p over p is 0. And that's p going to 0 from either side. So the overall limit, would exist. The reason I did y going to 0 plus is because of setting y equal to x squared. And you know what? I left something out that's important. I need to indicate that y is equaling x squared in this particular example, okay? So sorry about that. There's that. But anyway, and just as a recap, the limit x goes, assuming it exists, the limit x goes to c of the negative of f of x is the negative of the limit, assuming that the limit exists in the first place. If this one doesn't exist, then neither will this one. And the converse is also true. If this one does, then this one will as well. Okay. So, but anyway. Now here's a trickier example. Now sometimes, you remember, we allow for limits to equal infinity if they just go off in one direction. So the limit as x goes to either infinity. This means you can pick one. X isn't going to both. It just means either one you pick. So the limit as x goes to either infinity of this guy. Now the trick is to filter out x to the 80. And by the rules that I laid down a while back, the limit of the product is the product of the limits, as long as you don't have one of... It's okay for one of these guys to go to infinity as long as the other guy does not go to 0. We don't want infinity times 0, but otherwise we're good. And in fact, that does not happen, so we can break these apart. And in fact, these individual limits, they're both going to positive infinity, because x to the 80 is going to limit to infinity. X to the 20 is going to limit to infinity. And guys, the fact that we're subtracting 1, well, you can use the limit rules, and you can the difference of the limit is the limit of the difference, as long as both of these are not infinity. And they're not, because the limit x goes to any infinity of x to the 20 is positive infinity. The limit as x goes to any infinity of 1 is just 1, but positive infinity minus 1 by the rules we laid down is positive infinity. And likewise, this guy right here is positive infinity, because any type, either positive or negative infinity raised to the even power is positive infinity, okay? So we get positive infinity here, so that's positive infinity times positive infinity, which is equal to positive infinity, and we're done. There we go. And notice this limit is positive infinity right here, and this is positive infinity minus 1, which is going to be positive infinity. And so positive infinity times positive infinity is positive infinity. And I didn't put the pluses in front just out of laziness, okay? And I didn't, because if you put the pluses in front, you'll need to use parentheses when you multiply. So I just didn't bother. So there's that, okay? Just for convenience, I'm going to insert a definition here. If D is a non-empty subset of the reals, and if F is a function, this means the empty set right here, by the way. And if F is a function from D to R such that the absolute value of F is less than M for some M greater than 0, then it will be the case that then we will call F bounded on D. This is just a definition. There's no proof here, theorem, or anything like this. Is just a definition. And now, if D is a non-empty set, and if F is a function from D to R such that absolute value of F of X is greater than M for every M greater than 0, then F is said to be unbounded on D. And you know what? My unbounded definition needs adjustment. Let's see. I need to put for some X in D. Sorry about that, guys. So if D is a non-empty subset of the reals, and if F is a function from D to R, such that for every such that absolute F of X is greater than M for every M greater... You know what? This is badly worded. So let me reword this. Such that for any positive M... There we go. So I'll finally get it right. So if D is a non-empty subset of the reals, and if F is a function from D to R such that for any positive M, the absolute value of F of X will be greater than M for some X in D, then F is said to be unbounded on D. For any positive number, the absolute value of F will rise above that positive number for some X in the domain. Then X is not bounded on D, okay? That's what it means to be unbounded. That means you're not caged in. This one means you are. This one means you're not caged in. So I had to adjust my definition. Sorry about my unbounded there. I had to fix it. Okay, now here's a word of warning. the limit as x goes to infinity of this right here does not exist because we leave infinity minus infinity undefined for very good reasons. However, this limit right here does exist and it equals 0. And you're like, well, Jason, didn't you tell me that the difference of the limit is the limit of the difference? I did, but not for this. The limit of the difference is only the difference. The limit of the difference equals the difference of the limits only if both limits are finite or if the infinities have opposite signs. Here they don't. They have the same sign. We don't mess with infinity minus infinity. We leave that alone. You can't use the rules for infinity minus infinity. I never ever claimed that you could in the first place. The same thing goes for divide. Like if we had this limit divided by this limit, it wouldn't make sense. But the limit of x goes to either, actually this is true for either infinity, guys. Negative infinity, this would, if I replace my positive infinities with negative infinities, these rules would still be good, okay? Furthermore, if I replace minus with divide, this will equal 1, but this will be undefined. X divided by x goes to 1 here, but I can't say the limit x over the limit x. We can't do infinity divided by infinity, okay? And likewise, this limit does not exist even in the direction context, and neither does this one. It doesn't exist in the direction context either. But this limit right here will equal positive infinity, i.e. it doesn't really exist, but it does exist in the direction context, as we talked about earlier. If a limit equals infinity, at the end of the day, it doesn't exist, but it does have a direction. Well, let me put it this way. If a limit equals positive infinity, let's say, it does not really exist, but it has a direction. It goes forever up the y direction, so we say that the limit equals positive infinity, okay? We did that in videos past. But anyway, that's just a word of warning for you. And my examples are too close together. Let me space. The limit as x goes to 3 from the right. And I do need it from the right because the square, I don't want this to go below 0 in here, okay? So the limit as x goes to 3 from the right of this guy is equal to, now here's the trick. You got to do a little trick. You got to write x minus 3 as radical x minus 3 times radical x minus 3. And we can do that because we're assuming that x is bigger than 3 anyway. And then by difference of squares, you can break up the radical here. Let me finish this one on the next video. I'm running out of time. Thank you. I'll see you with this example on the next video.